Quantum memory for photons is like a super advanced storage system that can hold on to individual particles of light, called photons, without losing their special quantum properties. Think of a photon like a message in a bottle, but instead of a regular message, it contains quantum information, which can exist in multiple forms at once, like a spinning top that's spinning both clockwise and counterclockwise at the same time. Normally, storing a photon is tricky because light is constantly moving and delicate, like trying to hold onto a soap bubble without popping it. Quantum memory works by catching the photon and transferring its message into a safe medium, like a group of atoms, where it can be stored for later use. It's like freezing that soap bubble in time so it can be released exactly as it was when needed. This is important because photons are used to carry information in quantum communication networks. By storing them, we can keep quantum data intact even over long distances, making things like quantum computers more powerful and enabling unbreakable, secure communication. Without quantum memory, it would be like trying to send a fragile package across the world without any stops along the way. Chances are it would break before reaching its destination. Quantum memory is the safe stopover that ensures the message stays intact. Light isn't just a simple beam, it's a carrier of quantum information, a fundamental building block for the next generation of computing and communication. This is the essence of quantum memory, a technology poised to revolutionize fields like quantum computing and communication. Imagine a world where data is stored not in traditional bits, but in qubits. Instead of storing bits, the zeros and ones of classical computing, quantum memory stores qubits. These qubits are the quantum counterparts of classical bits, but with a twist. These qubits can exist in a superposition, simultaneously representing 0 and 1. This means they can perform multiple calculations at once, vastly increasing computational power. This unique property unlocks immense potential for processing information in ways unimaginable with classical computers. Quantum computers can solve complex problems that are currently unsolvable. Quantum memory acts as a crucial bridge between the quantum and classical worlds. It allows for the seamless integration of quantum data into our existing technological framework. It allows us to capture, store, and retrieve quantum information carried by photons, the particles of light. These photons are the messengers of quantum data, enabling secure and efficient communication. This ability is essential for building quantum networks that can transmit information with perfect security and enable complex quantum computations. These networks will form the backbone of future communication systems. By harnessing the power of light and the strangeness of quantum mechanics, we are entering a new era of information processing. This era promises unprecedented advancements in technology and science, an era where the very nature of memory is being redefined. Quantum memory is not just a technological advancement. It's a paradigm shift that will change how we think about and interact with information forever. Classical computers, like the ones we use every day, store information as bits. These bits are the fundamental building blocks of digital information. A bit represents a single binary value, either a 0 or a 1, much like a light switch that is either on or off. This binary system is the foundation of all classical computing. These bits are stored in electronic components like transistors, which act as tiny switches controlling the flow of electrical current. Transistors are the workhorses of classical computers, enabling complex calculations and data processing. Quantum memory, on the other hand, operates in the realm of quantum mechanics. This is a completely different paradigm from classical computing. Instead of bits, it stores qubits. Qubits are the quantum equivalent of classical bits, but they are far more powerful. Qubits can be thought of as quantum switches that can be both on and off at the same time, a concept known as superposition. This property allows quantum computers to perform many calculations simultaneously. Imagine a dimmer switch that can be set not just to on or off, but to an infinite range of brightness levels in between. This analogy helps to understand the flexibility and power of qubits. This ability to be in multiple states simultaneously gives quantum computers their immense power. They can solve complex problems much faster than classical computers, opening up new possibilities in fields like cryptography, material science, and artificial intelligence. One promising approach to creating quantum memory involves using atomic ensembles. Imagine a group of synchronized swimmers, each representing an atom in a confined space. When a photon carrying quantum information needs to be stored, it interacts with this ensemble. The photon's energy and quantum state are transferred to the collective motion of the atoms, like a ripple spreading through the synchronized swimmers. To retrieve the information, the process is reversed. The atoms release the stored photon, preserving its delicate quantum state. This method allows for the storage and retrieval of light-based quantum information, a crucial step towards building large-scale quantum networks. Another fascinating technique for creating quantum memory relies on rare earth ions embedded in crystals. These ions act like tiny magnets, and their quantum states can be manipulated with lasers. Think of these crystals as deep freezers for quantum information. When a photon carrying quantum information interacts with the rare earth ion, its state is transferred and frozen in the ion's magnetic orientation. By carefully controlling the interaction with lasers, the stored quantum information can be preserved for remarkably long periods, even up to milliseconds. This is a significant achievement, as it allows for the storage and processing of quantum information over practical timescales. Quantum repeaters, extending the reach of quantum communication with light. One of the most exciting applications of quantum memory lies in the development of quantum repeaters. These devices are crucial for the future of quantum communication. Quantum communication, which relies on sending photons over optical fibers, faces a fundamental limitation. Photons can be lost or scattered over long distances. This loss of photons can severely degrade the quality and reliability of the transmitted information. Quantum repeaters aim to overcome this challenge by dividing the transmission distance into smaller segments. By breaking down the journey into shorter, manageable parts, the integrity of the quantum information can be preserved. At each segment, a quantum repeater equipped with quantum memory stores the incoming photon. This storage process is critical as it ensures that the quantum state of the photon is maintained without degradation. It then retrieves and sends a fresh photon carrying the same quantum information to the next repeater. This process of storing and retransmitting photons continues until the information reaches its final destination. This relay race of photons allows quantum information to be transmitted over much greater distances, paving the way for a global quantum internet. Such an internet would revolutionize secure communication, making it virtually impossible for eavesdroppers to intercept the data. Decoherence and fidelity, the balancing act of quantum memory. Developing practical quantum memory is no easy feat. One of the biggest challenges is decoherence, the tendency of quantum systems to lose their delicate quantum properties due to interactions with their environment. Imagine trying to balance a spinning top on a shaky surface. The slightest disturbance can cause the top to wobble and eventually fall. Similarly, any unwanted interaction with the environment can disrupt the fragile quantum state stored in a quantum memory, leading to errors. Another challenge is fidelity, which refers to how accurately the quantum information is preserved during storage and retrieval. Achieving high fidelity is crucial for reliable quantum communication and computation. Quantum Internet, a network of entangled light. The development of practical quantum memory will unlock the door to a truly transformative technology, the quantum internet. Imagine a network where information is not just transmitted but teleported, using the bizarre phenomenon of quantum entanglement. In entanglement, two or more quantum particles become linked in such a way that they share the same fate, no matter how far apart they are. Measuring the state of one particle instantly determines the state of the other, as if they were communicating faster than the speed of light. By connecting quantum computers and other quantum devices through this entangled network, the quantum internet promises unparalleled speed, security, and computational power. Unbreakable secrets, quantum cryptography, and the power of single photons. Quantum memory also plays a crucial role in quantum cryptography, a revolutionary approach to secure communication that exploits the principles of quantum mechanics to create unbreakable codes. Imagine sending a secret message written on a series of polarized sunglasses. Each pair of sunglasses represents a single bit of information, with the orientation of the polarization encoding either a 0 or a 1. Eavesdroppers trying to intercept the message would inevitably disturb the polarization of the sunglasses, revealing their presence. Similarly, in quantum cryptography, single photons are used to carry keys for encrypting and decrypting messages. The future of quantum memory, from laboratories to our lives. The future of quantum memory is brimming with endless possibilities. As research progresses and technologies mature, we can expect to see quantum memory move out of the laboratory and into real-world applications, transforming industries. Imagine a future where quantum computers, connected by a global quantum internet, tackle challenges beyond the reach of classical computers, revolutionizing our world. Drug discovery could be accelerated by simulating complex molecules with incredible precision. Financial models could predict market trends with unprecedented accuracy, minimizing risks. Materials science could design new materials with remarkable properties, enhancing various technologies. The possibilities are as limitless as the quantum world itself, opening doors to a new era. Quantum versus classical memory, a head-to-head comparison. Classical memory and quantum memory represent two distinct approaches to storing information. Classical memory excels in its simplicity, scalability, and affordability. It has served us well for decades and will continue to do so in many applications. Quantum memory, however, offers something entirely different: the ability to store and manipulate the delicate and powerful world of quantum information. While still in its early stages of development, quantum memory holds the potential to revolutionize fields like computing, communication, and cryptography. As we continue to explore the strange and wonderful world of quantum mechanics, one thing is certain: the future of information storage and processing is quantum.